Good morning to every one of us. It's good to be back. In our last lesson, I said we are going to be discussing heat and temperature. So let's attend to it. What is heat? Heat is just a form of energy that makes things hot. Let's assume we have a pot on fire on our gas cooker, and when water is put into the pot, the gas cooker is switched on. Once the pot start becoming to be hot, it transfers that energy to the water and the water becomes hot. So the energy there transfers to the pot vis-a-vis the water. So it is just the process of making things hot through a particular energy. It should not be misinterpreted with temperature. There are two different things, and most students do make mistakes on that. So let's look at some examples. Fire gives heat. I told you, I gave you an example of a gas cooker with a pot. Water is in that pot. The energy is generated through the gas cooker and it is transferred vis-a-vis the pot to the water in the pot. So example is fire gives heat. The sun also gives heat. We'll be looking at that in the course of this lesson. The sun also gives heat, and hot water also gives heat. These are typical examples of heat as an example. Now, like I said earlier, temperature should not be misinterpreted with heat. Heat is a form of energy. Temperature tells us how things are hot or cold. When we put a bottle inside our refrigerator, it becomes cold. And when we put water in a pot, it becomes hot, when it starts boiling. So temperature tells us how much a particular object is hot or cold. So heat is a form of energy. Please take note of that. And temperature tells us how hot or cold an object could be. Please take note of the fact that the SI unit for temperature is Kelvin, and the instrument to measure temperature is referred to as thermometer. Very important. So one of those things JAM actually always tests is conversion of temperature sometimes from Celsius to Kelvin, which is the SI unit of temperature, and to Fahrenheit. So let's look at the relationship between Kelvin and Celsius. Celsius is also used to measure temperature, but the SI unit, standard SI unit for measuring temperature is Kelvin. So Kelvin equals Celsius plus 273. So peradventure you come across a question where it tells you what is the equivalent value of a particular body with a temperature of so Celsius. Please note that you need this formula. Kelvin equals Celsius plus 273. Let's look at some questions on that. Practice questions. Convert 27 degrees Celsius to Kelvin. Remember that Kelvin is the SI unit for temperature. So it is expected that you remember this formula, that Kelvin equals Celsius degree plus 273. Given the fact that we're given a Celsius degree of 27, therefore we're going to add it to 273 to give us 300 Kelvin. Another question is a common trap. Sometimes they give you temperature in Kelvin and tell you to find the equivalent value in Celsius. So the temperature of a body is 373 Kelvin. What is the temperature on the Celsius scale? Is a common trap. You just need to understand this formula, that Kelvin equals Celsius plus 273. So given the temperature in Kelvin, we should find it in Celsius. Recall the formula is Kelvin equals Celsius plus 273. Now, we have a 373 equivalent in Kelvin equals Celsius plus 273. And if we do the mathematical manipulation, we realize that Celsius definitely is going to be in 100 degree. Let's see if there are other examples. Yeah, this actually comes out almost all the time. I mentioned Fahrenheit. You must learn to know how to convert from Celsius to Fahrenheit and from Fahrenheit to Celsius. So we have a question here. Convert 20 degree Celsius to Fahrenheit. Now, they are not talking about the SI units. They just want you to convert between Celsius and Fahrenheit. The formula is simple. Fahrenheit is defined as 9 divided by 5 multiplied by Celsius plus 32. 9 divided by 5 multiplied by Celsius plus 32. So if you are given a question where you have the Celsius and you are asked to find it in Fahrenheit, please, this is a formula that you're going to use. Fahrenheit equals 9 divided by 5 multiplied by the Celsius degree plus 32. Now, given the fact that we have a Celsius in 20 degrees, now we should find F, the Fahrenheit. So we are now going to say 9 divided by 5 multiplied by 20. Recall that 20 here represents the Celsius value plus 32, and we are going to be having 68 Fahrenheit. So the conversion of 20 degrees Celsius to Fahrenheit will now be 68 Fahrenheit. You see, in most of questions in physics in JAM, it has to do with formula. Your ability to recall that formula has given you the chance to solve the question more than 70%. So if you are able to recall the formula that you're going to use, then you are good at solving the answer. Let's look at another question here. Which of the following temperatures represent the lowest possible temperature? The lowest possible temperature, as long as temperature is measured in SI units, the lowest possible temperature is 0 Kelvin, because Kelvin is the SI unit used to measure temperature, and the lowest possible temperature is 0 Kelvin. Yeah, it's because it is referred to as absolute zero. Thank you. Now, the difference between heat and temperature, like I said, heat is a form of energy, and temperature tells us how much a particular object, liquid or gas, is hot or cold. So we must know that heat is a form of energy, and temperature is the degree of hotness, how hot or cold. It depends on quantity. Yes, the amount of quantity, the amount of energy you apply will determine the heat that will be generated. But temperature does not depend on quantity. Please take note of that. The SI unit for heat is joules, and the SI unit of temperature is what? Kelvin. So as long as you recall that heat is a form of energy and temperature is the degree of hotness, you have actually solved one or two problems before answering any question on JAM. So let's look at some methods of heat transfer. Some methods of heat transfer, very important, very important. It comes almost all the time in JAM questions. Heat can move from one place to another in 3 ways. There are 3 basic ways heat can move from one place to another. First one is conduction. Conduction has to do with solid. Please take note of this. The heat transfer through solids is through conduction. Anything that is a solid, the method of heat transfer will be what? Conduction. The method of heat transfer will be conduction. Let's look at an example. When you put a metal spoon in a hot soup, it becomes hot. The soup is hot. You are putting a metal spoon in it. You can try it at home. You realize that the spoon suddenly becomes hot. There is transference of heat from that hot soup to that metal spoon, and so it becomes hot. So metal spoon is a good conductor. So let's look at heat from this way, there are bad conductors, there are good conductors. One of the good conductors is anything that is a metal, and that's why we are having our aluminum pot. When we put it on fire on our gas cooker, the heat is generated from the gas cooker. It transfers the energy it has conducted to whatever we put inside that pot. So metals, iron, copper, they are good conductors. Metals, example like iron, copper, aluminum, they are good conductors. What are bad conductors? Bad conductors are insulators. Bad conductors do not allow heat transfer through conduction. You know that conduction basically happens on a solid. So it happens on a solid, but we have bad conductors that cannot have the same value that metal a good conductor has, and one of them is wood. You can't transfer heat through a wood. It's going to get burned. It's not possible. And plastic, they are bad conductors. It is going to melt when you apply it to a plastic. It is going to melt. It's going to start melting. So they are bad conductors. Though they are solid, but they are bad conductors. They are actually called insulators. So if you are asked the question, what are insulators? Insulators are bad conductors. Please take note of that. Another method of heat transfer, this is now common with liquid. Heat transfer through liquids and gases are called convection. So I'm going back to that example. Heat transfer through liquid and gases are called convection. I'm going back to our boiling water. When we put water, when we put water inside a pot and we switch on the energy of our gas cooker, and the pot conducts the heat energy, it goes and the water starts boiling. Now the heat transferred to that water is called convection. So any form of heat that transfers through liquid and gases is called convection. The third way of transferring heat is called radiation. Yes, this is very popular. Heat transfer through sun rays. Now, it doesn't require a medium. Stay inside the sun. Stay under the sun for some time. When it is hot, you find out that your body start becoming hot, or you place something under the sun for some time, you realize that it suddenly starts becoming hot. This form of heat transfer is through waves. They don't require any medium. The first two require a medium. The first medium, it must be solid. Convection, it must be liquid and gases. But for radiation, it requires nothing. So when you stay under the sun, there is nothing, there is no medium between you and the sun rays. So, and you suddenly start exhibiting one form of heat energy. So heat energy from the sun is a typical example of radiation. Heat energy from the sun is a typical example of radiation. It is through waves only. No, just through waves only. No form of medium. It does not require any form of medium. So it's through waves only. So let's look for, I'm going to be looking at practical questions on that. But before going that, let's see the effects of heat and expansion of matter. Heat does so many things. It can cause expansion, change of state, and increase in temperature. Yes, our boiling water, our water was initially cool. The heat energy transferred through the pot goes into it and it starts boiling, and the temperature increases. That's one. Number two is expansion. If you go to our railways, a railway, where train passes, our railway track, once there is a certain level of heat, the tracks on the railway start expanding. So expansion of matter, most objects increase in size when heated, whether you like it or not. Put something under the sun, when it starts absorbing the heat through radiation, there is a certain increase in temperature, and there is also a certain increase in size. But when the heat is removed what happens is that there is a certain contrast, a reduce in size. You go back to the original size. So there are different types of expansion. We have expansion of solids, we have expansion of liquids, we have expansion of gases. This is what we will see almost on a daily basis. Let's look at an example. Electric wire sags on hot days. Yes, if we look at our electricity pole in front of our houses, you see that there are times when there is high sunlight, sunlight heat as a result of sun. You see that there is the tendency for some of those electric wires to fall. You think that they are falling down towards the ground. This is as a result of heat. And when we are during the rainy season, you will find out that this wire will never sag. They will never tend to fall because there is no heat. So please, you have to understand that heat causes expansion. It causes also what we call increase in temperature and change of state. So it is very common for JAM to ask questions as regard to this specific heat capacity. But we must know that we must understand that heat does not change its state. Just like in our previous topic when we talk about energy, energy only changes its state from kinetic energy to potential energy and from potential energy back to kinetic energy. It also only changes from one form to another. Heat changes from one form to another. If you have solid, put a solid inside a pot, like a cold block, and you apply a certain form of heat, you see it becomes liquid. That's melting. Even once it is at room temperature, it starts to melt. And when you apply additional heat energy to that liquid, it becomes gas, boiling, which is above 100 degrees Celsius. So if you put a solid inside a pot, like an ice block, and you apply energy to it, it starts to melt. And after it has become full-blown liquid, and you continue to apply energy to it, then it starts to boil. Now it turns to gas. So what I am actually trying to say is that it does not change. It only changes from one form to another. It is never lost. It remains it. So what then is specific heat capacity? Specific capacity, very common, is the amount of heat energy needed to raise the temperature of 1 kg of a substance by 1 degree Celsius. Please remember, it is just the amount of heat energy that is needed to raise the temperature of anything by 1 degree Celsius. You raise 1 kg of any matter by 1 degree Celsius, and it has a formula. The formula is written here. Specific energy, the heat energy, is defined as mass multiplied by specific heat energy, specific heat capacity, and change in temperature. When you apply it, recall that when we apply heat to a particular matter, maybe a solid, there's going to be change in temperature. Like I said, that it will cause an increase in temperature. So its specific capacity is defined as heat energy equals mass times specific heat capacity multiplied by change in temperature. Multiplied by change in temperature. Let's look at some practice questions on this. Very important that you take note of it. Practice questions on heat transfer and specific capacity. Heat is transferred from the sun to the earth mainly by radiation. It requires no medium. There is no need for any medium. And this kind of heat transfer is through what? Is through what? Is through waves. That's why it's called radiation. The handle of a cooking pot is usually made up of wood or plastic. Why? Because both plastic and wood are what? Insulators. They are bad conductors. In order to reduce heat by transfer, heat transfer by conduction. Remember that heat transfer through solid is basically conduction. So the handles of our pots, our cooking pot, is actually always made of either wood or plastic, because if it is made with metal or iron or aluminium, the heat will be transferred to the handle and it will also be hot. So that's why you see most cooking pots being the handle is made up of wood or plastic, because they are insulators, they are bad conductors. And any form of heat through a cooking pot is a solid, is called conduction. Which of the following expands most when heated? Look at that. Please, the answer is gas. Jam expects the other. You must know the other. They expand more than any other thing, and gas stands at the top of the pyramid. And that's why I'm giving you this hint here. Gas expands more than liquid, and liquid expands more than what? Solid. Gas expands more than liquid, liquid expands more than solid. If you put a cold block inside your pot and apply energy to it, it occupies a little space. But then immediately you apply energy and it becomes liquid, it occupies more space. And when the liquid is converted to gas, it occupies more and more space. So there is more expansion with gas. Take note. Gaps are left between railway tracks mainly to the reason is that during hot weather, the railway tracks where trains are passing, our trains do pass, is mainly made of metals, and during hot weather it will expand. That is why there are some gaps always left on the railway tracks. So on our railway tracks where train passes through, during hot weather, the ridges on that track are going to expand from the original size, and it's going to cause a gap on the railway tracks. And once the weather is cool, it contracts back. So two substances of equal mass receive the same quantity of heat. The substance with the specific capacity will, very technical. What is specific capacity? Specific capacity is the heat energy required to increase the temperature of a mass of 1 kg by 1 degree Celsius. And it is defined as heat equals mass times specific capacity multiplied by change in temperature. Here we are having a question that we have two equal masses. That means they have the same mass and the same energy is applied to them. What will happen when out of these two bodies, one has a specific heat up that is high? Definitely, it means that for the specific heat capacity to be high, there is a lower change in temperature rise. So this question is technical, but I want you to know that once there is a high specific heat capacity, then please note that the temperature rise is very low. So the substance with high specific capacity will have what? A lower temperature rise. And I'm giving you an hint here. Higher specific capacity implies heat up more slowly. That means the temperature rise is not high. Once the temperature rise is high, that means the specific heat capacity will be low. They are what I'm saying, indirectly proportional. Specific heat capacity is indirectly proportional to temperature rise. If there is an increase in temperature rise, the specific capacity will be what? Low. And if there is a high specific heat capacity, then the change in temperature rise will be low. So this a question on specific capacity. The quantity of heat required to raise the temperature. You see, once you see a question that says the temperature is going to be the temperature will rise, please note that it's a question on specific heat capacity. So the quantity of heat required to raise the temperature of a body by 2 kg mass 2 kg by 5 degrees Celsius. Now, the change in temperature is 5 degrees Celsius, is 10,000 joules. Calculate the specific heat capacity on the body. So the heat energy applied is 10,000 on mass of 2 kg, and the change in temperature rise by 5 degrees Celsius. So solution is, given the mass of 2 kg, change in temperature 5 degrees Celsius, the heat energy is 10,000 joules. Calculate the specific capacity. Recall that heat energy represented as Q equals mass times specific capacity multiplied by change in temperature. So if we now manipulate it mathematically by assigning the variables, 10,000 equals 2, which is the mass, multiplied by the specific capacity that we are looking for, and multiplied by change in temperature 5, we will get a 1,000. Now, the formula, the SI unit for specific capacity is joule divided by kilogram divided by Kelvin. How did we get that? Very simple, because you can actually see a question that says, what is the SI unit for a specific capacity? Recall that our heat energy is joule. It is going to be divided by kg. It's going to be divided by kg, and it's also going to be divided by Kelvin, and you could actually write it as J divided by kg multiplied by Kelvin. But when you now want to write it more properly, 1 divided by kilogram is the same thing as saying kilogram raised to power minus 1, and 1 divided by Kelvin is the same thing as saying Kelvin raised to power minus 1. So this is how we got the SI unit for specific heat capacity. So once you see a question talking about increase in temperature and you are seeing mass, you are seeing energy, it is likely it is going to be testing specific heat capacity. So we're going to be going further. Latent energy. Latent energy is referred to as energy. Latent energy is referred to as energy or heat that changes state of a matter without changing temperature. The state of a matter, the state maybe from solid to liquid, from liquid to gas without changing temperature, that's latent energy. So if the temperature does not change without changing temperature and there is change of state, then that's basically referring to latent energy. So latent energy will absorb heat. It will absorb heat, meaning melting, boiling, evaporation. It could release heat. Imagine you taking a cold chill which has become an ice block. Imagine you placing it on the table. We are not applying any change in temperature. There is no change in temperature. We are not applying any heat to it. Now it starts condensing. That means heat is being released. So latent energy is just the change of state of any matter without changing temperature. A typical example is ice melting into water. Bring ice out of the fridge, place it on a table, and it becomes water. Do you recall that the temperature, change the temperature? We are not applying any heat, but now it is becoming what? Water. So the formula, very simple formula, it is called heat energy equals mass times latent energy, specific latent energy. That's the formula, where M is mass, L is specific latent heat, and Q is what? Heat energy. Let's look at some questions. Which of the following processes involves the assumption of latent heat. And I gave an example there. We're having melting of ice. Temperature does not change. The temperature has never changed, but the state has changed. Now, you can't say that when you are now boiling water, you have applied heat to that. So there is no specific latent heat now. Because once you have applied an heat energy, the temperature increases from 1 to 2 to 3 until it gets to 100 degrees Celsius. So now temperature is changing. So there is nothing called latent heat. But for melting of ice, without applying any form of heat, and ice starts melting, and you put in a cold water, an ordinary water into a refrigerator without applying any heat, and it starts freezing. Now we can now start talking of specific latent heat. So let's look at this question. How much of heat energy is required to completely melt 2 kg, can you see that, of ice at 0 degrees Celsius, given you are going to be given this. Given specific latent heat fusion of ice at 3.6 times 10 raised to 5 joules per kilogram. So here it is talking about the heat. We have to generate, what's the heat applied? The heat applied to melt 2 kg of ice. So I recall that heat energy equals mass times latent heat, where mass in this question is 2 kg, and we have the specific latent heat. It has 3.6 times 10 raised to 5 joules per kilogram. We should find the heat energy. We are asked to find Q. So you are just going to input it there. 2 represent the mass, and given the value, you are going to be given the value. Don't assume. Don't bother yourself about this. You are going to be given the value of the specific latent heat, which is 3.36 times 10 raised to 5 joules per kilogram. And our heat energy required to melt 2 kg of ice at 0 degrees Celsius will now be 6.72 times 10 raised to 5 joules per kilogram. I want us to know that in the exam hall, you are not expected to take in your calculator, but there is calculator on our laptops. Let me see if I can quickly come up with one here where you can use. Yes, this is this one. This is one here. They are not expected. So we have a calculator where you can actually use on your laptop. You can actually make it scientific. You can also make it standard. So no student is allowed to bring in a calculator if you are doing mathematics, physics, chemistry, or any other, but you are expected to use the calculator on your laptop. Just on your search bar, I'm going to show you again. On your search bar on your calculator, just type calculator. You don't need to stress yourself, and use your mouse to click on it, and the calculator pops up where you can do any form of calculation that you like, and it gives you your answer. So that's just by the way. We'll be going to thermodynamics. So what's the study of heat and energy? It is referred to as thermodynamics. The study of heat and energy is called thermodynamics. The study of heat and energy is called thermodynamics. So we have the first law of thermodynamics, which is often always tested in JAM. The first law of thermodynamics says that heat supply equals change in internal energy plus work done. There is going to be once there is a form of heat supply, there is going to be change in internal energy, and a certain work is done. So the simple meaning is that no, heat and energy are never lost. They are always conserved. They are always changed. They are never lost but conserved. So it's not as if you are going to lose a form of heat or energy. So if you don't recall what the first law of thermodynamics says, please know that it's telling you that energy is always what? Conserved. It's just the conservation of energy. And it has a formula. The heat supply will amount to change in internal energy plus work done. The heat supply will amount to change in internal energy plus work done. So let's look at the question. The first law of thermodynamics is a statement of principle of conservation of energy. that energy is conserved. Energy is neither lost or created, it is always conserved. So, according to the first law of thermodynamics, when heat is supplied to the system, the heat energy is used to do. It's just actually testing your knowledge on that formula. Once, according to the first law of thermodynamics, when heat is supplied, once it is supplied, it will cause change in internal energy with work done. So the answer is do work and increase in internal energy. Once it is supplied, the first law, it says, according to the first law of thermodynamics, once it is supplied to a system, it will cause work to be done and change in internal energy. So that's just the answer. Let's look at calculations on thermodynamics. A gas absorbs 500 joules of heat and does work of 200 does 200 joules of work. A gas absorbs 500 joules of heat and 200 joules of work on its surrounding. Calculate the increase in internal energy of the gas. So once you now start seeing internal energy, you know you are being tested on thermodynamics, the first law of thermodynamics. So let's look at the question, the solution. Given the amount of heat supplied, the amount of heat supplied is what? 500 joules. The work done is 200 joules. And the change in internal energy is what is expected for you to calculate. Recall that heat supplied equals change in internal energy plus work done. And since we have the heat supplied to be 500 joules, the change in internal energy is what we are asked to calculate, plus 200 joules, which is the work done. Then the change in internal energy will be in 300 joules, 500 minus 200 joules. So please, oftentimes JAM always tests first law of thermodynamics, and I told you one of my major purpose of actually creating this channel is to assist anybody who comes across this channel on areas you should focus on when studying for physics in JAM, where they concentrate their questions on. So please, that you recall that you must know some formula from specific heat capacity to specific latent energy. Please know this formula. And first law of thermodynamics, which talks about law of conservation, which is basically the heat supplied equals change in internal energy plus work done. So let's look at some practice questions. Heat is a form of energy. Yes. Heat transferred through direct contact. It's called what? Direct contact. Direct contact. Conduction. Radiation, it requires no medium, and that's through waves. Convection, it has to do with liquid and gases, while conduction through solids. And direct contact, I gave an example of a pot on a gas cooker. The boiling point of water in Kelvin is what? Recall, this question is very funny. If you end up saying 100 Kelvin, you are wrong. Kelvin is the standard SI unit for measuring temperature. Kelvin is standard SI unit for measuring temperature. But when you put water and it starts boiling, water starts boiling at 100, it becomes at 100 degrees Celsius. So you could see that you were not given a value of 100 degrees Celsius, but it is just a logical question. So the answer to this will be what? The boiling point of water in Kelvin is to understand that 100 degrees Celsius must be converted to what? Kelvin. 100 degrees Celsius, because water starts boiling at 100 degrees Celsius and is converted into gas, and so you have to now convert it into Kelvin. Thank you for listening. Our next class will be discussing waves and sound. Like I said, this guide is not necessarily to replace your learning curve. It is to assist you so that you don't read and miss, and you understand what is expected for you while preparing for UTME physics. Thank you, and do Have a nice day.